Hey, what's up, guys? So today I want to talk about the sheafification. So if you haven't seen my video, the previous three videos about stocks and sheaf theory, and you can check out. Okay. So hope you guys subscribe to my channel. So today I want to talk about sheafification and what hell it is. Okay. And the so basically I remember that the first time I heard about sheafification, I don't understand it, and it's very weird that I mean I feel like very hard to understand what the hell is sheafification. Okay, so in this video that I try to uh say what I understand sheafification and give the detailed proof. So I will prove. So I will not do the detail as detailed as possible, not like textbook. So textbook will tell you that you just check whatever it is. So yeah. Okay, so hope you guys subscribe to my channel. Okay, so the idea is that so maybe the first time you heard about sheafification is that somebody says that, oh, there's a definition called presheaf. You start from some topological space X and then a contravariant functor and then f of u, maybe a abelian group, ring, or module or whatever. And there's a more restricted guy called sheaf. Okay, then you heard about there's a lot of theorem about sheaf, and you can talk about morphisms between sheaf, and you can talk about idea called stalks. Okay, so stalks is very important that we will keep using it. So let me just recall that stalk is that for every f of every x that you take us, where x belongs to u and s belongs to f of u, and there is a modulo some equivalent relation if us and vs prime is the same if there is an open subset between u intersection with v, such that there's a restriction. So if S restricting on W is the same as S prime restricting from V to W. Okay, so sheaf, and then there's a amazing results called the sheafification. So sheafification tell you that if somebody give you a presheaf, then you can create a guy that's called F sharp. This guy is a sheaf. So F is a presheaf, and this guy is a sheaf. And there are two amazing property. The first property is that the sheaf and the sheafification, they have the same stalks, or basically their stalks are isomorphism. Okay. The second one is that the second one is more strange, right? Second one says that if you have a presheaf and go to some sheaf, okay, then there's a universal property that there's a unique factorization or unique map from F sheaf, the sheafification of F to G. So it's like any given this map, right? There's a map, strange map, this guy, right? There's a this guy exists such that the this guy commute. Okay. So this is a universal property of sheafification. Universal property of sheafification. Okay, so this video I will tell you that what the hell is sheafification and why it is the following two are true, or maybe more. Okay. Okay, so we want to start at the beginning, and the beginning is very difficult. So if you don't understand this definition, then you should stop the video or you start video and just think about it because it will make. I mean, otherwise that you will not learn anything. Okay, so given a sheaf, so F is a presheaf. You define the F sheaf, right? F sheafification of F on U, where open Z. Or take X to be a topological space and use a subset of X, open subset. You define to be SU. Okay, so now it's very important. I just say SU, which belongs to the products of the each stocks. So now remember that so FU is a stocks, right? I take product set of these stocks, and for every product set that I take the SU. Okay, so this SU for each U, right? So these SU are the subset of the product set. Okay. So you can imagine that this SU has maybe uncountable component. Okay, uncountable component such that such that there is some star. Okay, so let me write a star. Okay, so star says that for every u belongs to u. Okay, there is this open neighborhood V. Okay, so there is this open neighborhood V, and the section belongs to f of V, such that for all, let's say nu belongs to V, we have, okay, so it's this, right? We have u, right? And then we have, so for every u, there's a open set V, and such that for, and then there is a section, right? So section is sigma per on the f of V, such that for every nu belongs to V, we have S nu. So notice that this S nu are the points which inside this sheafification should be equals to V sigma. So V sigma is, as I said, right, can be represented as the equivalent class of Fx, right? So V sigma can be represented as a stalks in a S nu, right? So this guy is the same in F nu. Sorry, V sigma can be viewed as a representative in F nu, right? So what I'm saying is that this S nu so this F u, right, will be the infinite products, such that given any there's a so F nu is a set of all infinite products or infinite products such that it has this weird property such that for every u belongs to u, there's a open set V. For every nu belongs to this V, this S nu is this guy, right? It's a product set. This S nu on these new points will be the same as V sigma in F nu. Okay, so hopefully you understand this definition. Okay, so what? Okay, so the first thing that I want to say is that okay, so before we keep doing this, let's maybe recall a simple fact. Okay, so this simple fact is that let's see. Okay, so there's a simple fact. Recall that I define previous video that I can say I define a map from f of u to the products of x belongs to u and the stalks. Okay, the definition is very simple. You're given S, right? You just map into the representative. As I say, the representative of stalks is the open set and S, right? So, so what is the natural, right? Well, this is the natural map, right? So given S, I just say US. Okay, I just very simple. That you give me S belongs to FU. I just say US, right? S belongs to U. Okay, and this map is injective. If you don't know why, you can check my previous video, injective. Okay, so what I want to say is the following. So there's a canonical map, or there's a map, canonical map. So given F, we can have this, right? So let me just use the pi of F. So pi of F is another sheaf from U to this. Okay, so this guy is a sheaf. If you don't know why, you can check out my previous video. So this guy is a sheaf. So there's a map that from from F to the F presheaf and product sheaf. Okay, and I forgot to say about a restriction map. So this is a set of sheaf, right? So what is a restriction map? Very trivial, right? If somebody gives you V is a subset of U, then all you need to do is just forget the coefficient, forget the component which is not in V, right? So restriction map is very simple, right? We just define if you, right, you start from you get a subset, right? So you have a natural map, right? From F U belong to U, go to V belong nu belongs to V, F nu, right? And since V is a subset of U, so you just preserve what you have. So in this way, that you just forget about a component which is not in V. Okay, so there's a map from f sharp f or sheafification to product f, and so obviously that we already have this map, right? As I just defined this map. Okay, and so this map is also very simple, right? So I can define this map. So I can define the same thing. I can define this as to the x belongs to u, us, right? And then these guys also in this map just directly this guy's this guy is a subject has more constraint, right? So this guy is injective, right? This guy is injective. This f sheaf location we have not yet proved is a sheaf, but obviously this must be a sub presheaf. Okay, so we have this, and as I said, we can have this. So we have this. Okay, so we have this. Okay, so the question is that why this is true, right? I can define S to be product of x u us, and I need to check that this satisfy these results. Okay, so let me just maybe I put it here. Hopefully it's simple for you. Okay, so you can I can take su, right? In this case to be just us. Okay, and then I check where this is true. Okay, so I say that for u belongs to u, is this u belongs to v, right? So in this case, I choose v should be u, right? So this sentence become for belongs to u. There exists the u belongs to u, and the sigma fu. I just choose s, so I just choose s. I choose s to be f of u, or to be element of fu. Then for all new belongs to v, we have s new belongs to v sigma in f new. Okay, but this is stupid, right? Because each su is already defined to be us. Okay, so this is trivial. Okay, so now this means that given f, then we have the following map: f go to the sheafification of f, then the product f. Okay, so this is the first results that you need to remember. Okay, there's this map. Okay. Okay, so now we're gonna to go to the important part. Sheaf of f star, f sharp is a sheaf. Is a sheaf. You can think a little bit and why this is true. Okay, but let me just quickly prove. Actually, proof this is not difficult. There's another proof which is more difficult. Okay, but this one is simple. Okay, so let's take u. Let's take some open cover. Okay, and so we take si. We can take si, right? So si is a siu. Remember that u and the u belongs to ui, right? Because the product set between the f sheaf. Okay, and then we need to say that if first, okay, so first one, we need to say that if they agree on each other, then there will be a restriction, right? Will be a restriction. Okay, so we say that suppose si and sj agree on ui intersection uj, then we hope to find that s such that s restricting to ui is the same as si, right? But this is trivial. Okay, the reason is that previously we already proved that this guy, right? This guy is a sheaf, right? So now this guy, since this guy is a sheaf, right? So by definition, right? I can find s such as x restricted to ui to be si, and then s restricted to uj will be sj, since these guys are sheaf. Okay, so the rest is to show this s has this property, right? This weird property, right? Because now we already proved that we can find s such as restricted to ui is si, s to uj is sj, and we need to show that this s has this star property, with weird property that we need to satisfy. But this is also trivial. Okay. The reason is that this condition is local, right? So for example, let's say, right? So if I take let's see, so I pick u belongs to u, right? Then there will be I, such that u belongs to ui. Okay, but I know that X restricted to UI is SI. So I can choose, right? So I can choose, right? I can choose V belongs to, so given for every U belongs to UI, that there's always a V, whatever, blah, blah, blah. And this condition is basically just locally already satisfied on UI, okay? So the condition is already satisfied on UI. Condition is already, this condition is true, right? it's already true on UI. So this S will have this property trivially, right? Because this condition is local. You already proved that. You already know that each SI has this property. So if you have S which localized, which you restrict to SI, then obviously if you shrink this open set to be smaller, such that if you shrink this open set to be V cover U and in UI, and this V already have that kind of property. Okay, so these two are almost trivial, or just trivial. Okay, so now you prove that. You prove what? You already proved that this guy is a sheaf. So what's the next? Okay, so theorem 2. Actually this one is the difficult one. Okay, or maybe you need to think a little bit. So we need to prove that their stalks are same. Okay, so proof. So like a standard proof, right? So I mean we have a map, right? F sheaf, and then what we did is that someone gives you S, right? Then you're happily just say that, oh, it's you and you. You're happy to say that, oh, I just take this. Okay, so we want to prove that it's equal to phi, and then we want to show that phi is injective and surjective. Okay, so first one, phi is injective. How do we prove this? It's basically trivial. The reason is that trivial. The reason is that why? The reason is that we already proved, right? Remember that I said there's a beautiful map, and then we prove this map is injective, and this map is also injective. Okay, so you can use your simple set theory argument to prove that this guy is injective. Otherwise, that if they are not injective, then they map to the same guy, then this guy will be the same guy, which violate this guy is injective. So this map is injective. So phi is injective. Okay, so the second one is that phi is surjective. So as we have another theorem about if you have two sheaf, their isomorphism and stalks, then they will be the same sheaf. This proof, the proof is difficult on surjectivity. So this is like I mean, sometimes the surjectivity is always difficult to prove. I mean, in this kind of case. Okay. So we need to say that phi is, we want to prove that this guy is surjective. So it's very, let's take S bar, right? Let's take S bar to be the fx. Okay. So now the problem is that what is S bar look like? Okay. Actually we don't know, right? So we only know that S bar looks like, I mean, S bar has an infinite infinite as a U, has the infinite coordinates, right? S bar U, and has weird property. Okay. Okay. But let's write S bar. Okay. So this, oh, by the way, sorry, this is not correct. So let's take S bar in the sheaf, stalks of sheafification of X on U. So now S bar looks like what? So remember, should be viewed as a US, right? But now S belongs to F, right? Sheafification U. Okay, so S has infinite coordinates, right? So S X and new, right? And it has the weird property. Okay, has this weird property. Okay, then by definition, right? By definition, we know that there's an open set V of X, the section sigma belongs to f of v, such that when s restricted to new, right, will equals to sigma, will equals to what? Notice what is s looks like. S has property, right? So when s, so s new has an infinite coordinate, right? So when s restricted, now each s restricted to new, so s has infinite property, has infinite component, right? So let me just write down. So when s restricted to new, then each su is the same as each su restricted to new, right? But okay, but the weird property is that since s restricted to new, by definition, each component restricted to new will be the v sigma, right? V sigma will be the v sigma. Will be the v sigma, right? So will be the v sigma, right? For each, so let me just let's say this is for each. So S new has infinite component U new, right? Has infinite component U. If you force S this to be a subset, then restricting of SU, restricting on the subset of V, let's say, okay, yeah. So this one is hard to say. Let me just write in this way. So this property tell me what? Okay, so this property tell me that let me just write down, right? This property tell you that there's a v belongs to sigma of x, sigma of such that let's say s. Okay, so this such that s, right? S new will be the same as v sigma, right? In f new. Okay, and so if you restrict it, okay, so yeah, so this is sheaf of, right? So this guy looks like this. Okay, so but what this means is that if you restricted S, right, into V, okay, if you restricted this S, the sheaf of U, right, into V, then this is the same as, since this is the same as you restrict on V, right, but for all V, okay, so this guy is basically says that new becomes to V for S new, but this is the same as new belongs to V for V sigma, okay. But so this is true, right? In the product of f, right? But this tell you that this x restricted to v is the same as this. Okay, so this v sigma is what we want, right? Because now we find that we find the map. We find if we choose v sigma, then we choose a v sigma, and this is v sigma, right? V sigma. So sigma is what we want. Okay, so sigma is what we want. Okay, since sigma map into the will become the new belongs to v sigma. Okay, so phi is surjective. Phi is surjective. Okay, so you can see that just write down you just write down definition and try to prove by yourself. It's not difficult. Okay, so I think now we have proof whatever I said. So we have first one, sheafification is a sheaf. This one is almost trivial by the if you already proved that the product is a sheaf. And then this guy is also, and then you prove that their stalks are the same. Okay. And the third one, you need to prove the universal property. Okay, so recall that we have a theorem that I proved in the previous video. If you have two sheaves, then for all x they are isomorphic, then you can prove that f is isomorphic to G. If and only if. Okay. So basically, it's just if you have isomorphism as a sheaf morphism, basically you can find the phi such that it maps is bijective and bijective. Then then definitely it will induce the same as stalks. If you have this kind of map which induces bijective out of stalks, then you can prove that these two are the same as a morphism. Okay, this isomorphism is sheaf. Okay, so this is the theorem that we need to use. Now let's prove the universal property. Okay, and I have another theorem which is simple, so I think you can check. Maybe you don't need to check. So a theorem is very simple. If G is let's say if G is a sheaf, then if you do the sheafification, then you will the same as previous one. Okay, so a proof is just one line, right? Because this guy is a sheaf, this guy is a sheaf, right? So, and then we already proved that their stalks are the same. And then there's a natural map from G to G, right? As I say, there's a natural map from here to here. So obviously that they already induced the same thing on all the stalks. Then by the previous theorem that this guy is a sheaf. Sorry, and this guy is isomorphic to G, right? Because we just proved that for every stalks they are the same. Okay, so final theorem is what I want to prove is a universal property of sheaf. Okay, so what we're gonna to prove is that somebody gives you f, right? You want to prove that f factorized through sheafification of f. So let's take the following two diagram, right? So we have f to obviously we have f to f sheafification and this guy. Now let's say we already have a sheaf and G. Let's call it sheafification. So this guy is a sheaf, and there's a product G. And obviously that if you have a morphism of this, then you will introduce a morphism of this, and you will introduce a morphism of this, right? These are maps to stocks. These are maps to stocks. Okay, so simply speaking, that since these two are already the same, right? So they are bijective, right? This guy is bijective, as we just proved, right? If G, since G is a sheaf, so if you map F sheaf to G sheaf, then it's the same as you just map F sheaf to G. Because these two are the same, right? You can just composite this map or whatever you want. So it's the same as you have this map, right? So this factorized trivial. Since we proved that if G is a sheaf, then sheafification of G is already a sheaf. Okay, so proof done, right? Because you can think there are isomorphism, right? So whenever you have F sheaf map to G sheaf map sheafification, then basically they will simply induce this map. Okay, so hopefully this video helps and prove all the important property of sheafification. And so next time that if someone asks you, you can say a little bit about sheafification and not just afraid and not afraid of this guy. See you next videos.